Qualitative assessment of pipework vibration, analyzing vibration impacts on industrial piping systems. Purpose, scope, and application. The qualitative assessment of pipework vibration is a preliminary method designed to identify potential risks of vibration-induced fatigue failure in piping systems. Its primary purpose is to provide a structured approach for determining the likelihood of failure, LOF, and prioritizing areas that require detailed quantitative analysis. This assessment is applicable to new designs, existing plants, and modifications to existing systems. For new designs, it helps engineers anticipate vibration issues before construction begins, leveraging lessons learned from similar projects. For existing plants, it serves as a diagnostic tool to evaluate operational conditions and historical vibration problems. When changes are introduced to an existing plant, such as process modifications or equipment upgrades, the assessment ensures that new configurations do not introduce unforeseen vibration risks. The scope of this methodology includes evaluating excitation mechanisms, operational factors, and construction quality, all of which influence vibration behavior. By systematically applying this approach, organizations can enhance safety, reliability, and operational efficiency while minimizing downtime and costly failures. Assessment methodology, excitation and condition factors. The methodology for qualitative assessment combines two primary sets of factors, excitation factors and condition/operational factors. Excitation factors include mechanisms such as flow-induced turbulence, pulsation from reciprocating machinery, cavitation, flashing, and surge caused by fast-acting valves. Each factor is scored as high, medium, or low based on its potential to induce vibration. Condition and operational factors, such as construction quality, maintenance effectiveness, cyclical operations, and frequency of process upsets, are also evaluated and assigned a score. These scores are aggregated to identify critical areas requiring further analysis. The process involves reviewing design documents, operational history, and conducting visual inspections for existing plants. Flowcharts provided in the guidelines illustrate how these factors interact to produce a prioritized list of systems for quantitative assessment. This structured scoring system ensures consistency and objectivity, enabling engineers to focus resources on the most significant risks. Excitation factors. Number 1, fluid kinetic energy. Meaning, higher fluid velocity or density increases energy in the flow. Why it matters: creates stronger turbulence impacted to higher pipe vibration risk. For gases impacted to larger pulsation forces. For liquids impacted to higher surge pressure during valve closure. For special note, sometimes the highest fluid kinetic energy comes from bypass/recycle lines that don't appear on PFDs. These should be checked. Excitation factors. Number 2, choked flow or sonic velocity. Meaning, gas reaches sonic velocity at restrictions, valves, orifice plates. Why it matters: produces high-frequency acoustic vibration. Shock waves may form downstream, causing acoustic fatigue. Excitation factors. Number 3, rotating or reciprocating machinery nearby. Meaning, pipework connected to or close to mechanical equipment. Why it matters: reciprocating machines create strong mechanical excitation. Rotating machines may also transmit vibration. Rule of thumb for close: offshore, same deck or module, above or below. Onshore, within radius equal to skid length. Excitation factors. Number 4, positive displacement pumps or compressors. Meaning, equipment that pushes fluid in pulses. Why it matters: can generate significant pulsation-induced vibration. Even screw compressors sometimes show pulsation issues. Excitation factors. Number 5, centrifugal compressor rotating stall. Meaning, compressor operating at low flow impacted to unstable blade behavior. Why it matters: produces pressure pulsations impacted to high vibration risk. Note, vibrations may occur when operating near surge line unless anti-surge controls work properly. Excitation factors. Number 6, cavitation or flashing. Meaning, liquid turning to vapor due to pressure drop or temperature increase. Why it matters: flashing, sudden volume change impacted to transient vibration. Cavitation, collapse of bubbles impacted to intense vibration. Check areas with significant pressure drops, valves, orifice plates, pumps, fluid mixing points, increased temperature approaching vapor pressure, excitation factors number 7, fast-acting valves. Meaning, automatic valves that open/close quickly. Why it matters: fast closure in liquids impacted to surge pressure, high transient vibration. Fast opening impacted to sudden momentum change. Valves to assess: ESDV, FCV, PCV, fast closing, BDV, RV, fast opening. Manually operated valves can be ignored, excitation factors number 8, intrusive elements, thermal wells, probes, etc. Meaning, objects inserted into the flow. Why it matters: may cause vortex shedding impacted to vibration and potential failure of the probe, excitation factors number 9, slug flow potential. Meaning, liquid-gas multiphase flow with intermittent slugs. Why it matters: creates severe unsteady forces and transient vibration. Recommendation: seek specialist analysis due to complexity, excitation factors number 10, history of vibration issues. Meaning, previous similar systems or existing plant history show vibration problems. Why it matters: indicates higher likelihood of repeat failures. Check whether previous corrective actions were effective and applied across full operating envelope. Condition and operational factors number 1, construction quality. What it means: how well the piping was fabricated, welded, supported, and installed. Impact on vibration: better than industry standard, impacted to low risk. Well-built piping handles vibration better. At industry standard, impacted to medium risk. Normal construction may have typical weak points. Below industry standard, impacted to high risk. Poor welds, poor alignment, or bad supports greatly increase vibration fatigue risk. Condition and operational factors number 2, maintenance and corrosion management. What it means: how well the plant maintains equipment, performs corrosion checks, and repairs defects. Impact on vibration: better than industry standard, impacted to low risk. Good maintenance prevents deterioration that could worsen vibration. At industry standard, impacted to medium risk. Typical maintenance: reasonable but not exceptional. Below industry standard, impacted to high risk. Corrosion, thinning, or loose supports can worsen vibration and lead to failure. Condition and operational factors number 3, cyclical operations. What it means: whether the system experiences repeated operational cycles, batch processes, frequent flow or pressure fluctuations. Impact on vibration: no cyclical operations, impacted to low risk. Steady operation equals less fatigue accumulation. Yes, there are cycles high risk. Repeated cycles cause recurring dynamic loads, accelerates fatigue. Condition and operational factors number 4, unplanned process interruptions. What it means: how often the plant unexpectedly stops or trips. Impact on vibration: 0 to 1 interruptions per year, low risk. Stable operation with minimal disturbances. 2 to 8 interruptions per year, medium risk. Some upset conditions that may cause higher vibration events. 9 interruptions per year, high risk. Frequent upsets, more high amplitude transient loads and higher fatigue risk. New design considerations, existing plant and change management. For new designs, qualitative assessment focuses on predicting potential vibration issues before construction. Engineers should review similar projects and incorporate lessons learned to avoid repeating past mistakes. The assessment prioritizes systems that are safety critical or business critical, ensuring that these areas undergo detailed evaluation. Factors such as anticipated fluid velocities, machinery configurations, and valve operations are analyzed to identify excitation mechanisms. By addressing these issues early, designers can implement mitigation measures such as optimized piping layouts, improved support structures, and vibration dampening devices. This proactive approach reduces the likelihood of costly retrofits and operational disruptions after commissioning. For existing plants, the assessment begins with a visual inspection to identify as-built conditions and any signs of vibration-related damage. Historical data on vibration incidents and corrective actions are reviewed to understand recurring issues. When changes are proposed, such as process modifications or equipment upgrades, the assessment evaluates whether these changes could introduce new vibration risks. This includes analyzing variations in flow velocity, fluid properties, and operational configurations. The process integrates with hazard and HAZOP studies to ensure comprehensive risk management. By systematically addressing these factors, operators can maintain plant integrity and prevent failures during operational changes. Key excitation sources, condition and operational influences. Excitation sources are the primary drivers of vibration in piping systems. These include flow-induced turbulence, which occurs at high fluid velocities, and pulsation from reciprocating or rotating machinery. Cavitation and flashing in liquid systems can generate transient vibrations due to sudden phase changes. Fast-acting valves, such as emergency shutdown or blowdown valves, can cause surge forces and momentum changes. Intrusive elements like thermowells may lead to vortex shedding, while slug flow in multiphase systems can create severe dynamic loads. Identifying these sources is critical for determining which systems require quantitative analysis and implementing design or operational controls to mitigate risks. Condition and operational factors significantly affect a system's susceptibility to vibration-induced fatigue. Poor construction quality can compromise structural integrity, while inadequate maintenance and corrosion management exacerbate weaknesses. Cyclical operations, such as batch processes, introduce repetitive dynamic loads, increasing fatigue risk. Frequent process upsets or unplanned interruptions can cause transient high-amplitude vibrations. These factors must be considered alongside excitation mechanisms to provide a holistic assessment. By improving construction standards, implementing robust maintenance programs, and minimizing operational variability, organizations can reduce the likelihood of vibration-related failures. Results and next steps. The outcome of the qualitative assessment is a prioritized list of systems based on their vibration risk profile. Systems with high or medium scores for excitation factors or operational conditions are flagged for quantitative analysis using advanced methods outlined in subsequent technical modules. This prioritization ensures that resources are allocated efficiently, focusing on areas with the greatest potential impact on safety and reliability. The process also identifies specific excitation mechanisms that require mitigation, guiding design improvements and operational adjustments. Ultimately, this structured approach enhances plant integrity, reduces downtime, and supports compliance with industry standards.